I am Ruhuna from IESL Mechanical Engineering Sectional Committee. I warmly welcome you all for the today's MED lecture. This program will be live streaming throughout the 45 minutes next. Today the topic is Introduction to Meshfree Models and their Applications, a novel trend in numerical modeling of engineering problems. Since this program is webcast, I welcome the live streaming audience for the session. I will introduce the lecturer, Dr. Chaminda Karunasena, Senior Lecturer, Department of Mechanical and Manufacturing Engineering, Faculty of Engineering, University of Ruhuna. Dr. Chaminda obtained his first professional qualification from University of Moratuwa in 2006, graduating as a mechanical engineer with first class honors, obtaining the class rank number 1. With his excellence in undergraduate studies, he could secure many honors and awards, including the gold medal and the National Development Bank Award for the outstanding performance in mechanical engineering degree examinations. As fresh graduate, he joined Loadstar Private Limited, Sri Lanka, as an engineer, and later he was promoted to a change leader, where he served in different engineering related productivity improvement projects. By the end of 2009, he joined Department of Mechanical Engineering, University of Ruhuna, as a lecturer. In the meantime, he completed his master's studies at University of Moratuwa, specialized in industrial automation. In 2011, he started his doctoral studies at Queensland University of Technology, Brisbane, Australia, and graduated in November 2014. During his doctoral studies, he was awarded the Outstanding Postgraduate Student Award from the university, and his thesis is currently shortlisted for the prestigious Outstanding Thesis Award of Queensland University. After his doctoral studies, he has returned to the country and has resumed duties as a lecturer attached to the same department of the University of Ruhuna. His research expertise mainly involves Meshfree methods, and he authored many publications for international indexed journals and conferences. At present, he is also actively involved in collaborative research work as visiting fellow of Queensland University of Technology, Australia, where he mainly focuses on applications of Meshfree methods in biosystems, such as plant tissue modeling. Other than this interest in fundamental research, being a mechanical and automation engineer, he is highly interested in developing renewable energy extraction methods from green sources such as ocean, wind, and biofuels. This is a brief description about Dr. Chaminda Karunasena. This is over to you. This session will be continued 45 minutes of presentation and then another 45 minutes of panel discussion. Over to you, Chaminda.
Thank you so much for the generous introduction, and I'm Chaminda, as he introduced, so I warmly welcome you all for my presentation. The topic today is Introduction to Meshfree Methods and their Applications, a novel trend in numerical modeling of engineering problems. The basic idea behind today's presentation is to introduce what are these new trends, what are the basics of these so-called Meshfree methods, what are the potential applications, and things that are done in research front currently. So the presentation outcome contents, basically we'll discuss on the numerical modeling and simulation, the overall, doesn't matter it's a Meshfree or any other method. Then we move into the basics of Meshfree methods, and particularly we'll discuss on smooth particle hydrodynamics, which is a key technique in this particular method, which is I am also have some expertise. Then I'll show you some basics of how to run a simulation with Meshfree and some applications, basically videos. You can see a couple of videos. Then I'll give you some brief introduction to what are the ongoing research in basically biosystems engineering, tissue modeling, and so we'll finish with conclusions and outlooks towards that. Yeah, so to begin with, the basics of numerical modeling is, why we use basically the intent is we study a given problem in its simplified version. What does that mean? In numerical modeling, it's so hard and expensive to model a real system as it is. So what we do, we simplify the problem first, then we do an accurate model on that simplified design. So that is common to finite element or any other method, mathematical modeling. So the simplification is done in order to easily relate with available theory. So if there's some common theory, we try to simplify in order to match with the theory. If not, for instance, like in doctoral studies or so forth, we can develop our own theory to match with the concept. And then once we are ready with the model, we can do some computer coding. Usually these runs in computers, and we can run a suitable program. Then we observe our results, and sometimes we need to adjust the parameters to get the desired result. That is general for any numerical modeling. And we need to be clear on the basic 3 stages in whatever the numerical modeling, which is the basic modeling task, and we need to validate our work using some experimental pre-known experiments. If some people have done some experiments, we run our simulation until we get the same results. Then our thing is correct. That eventually we use for prediction, for unknown things. People may have not seen it, but we can simulate such a thing, which is called prediction. Why we use numerical modeling? Can't we keep on doing experiments? Basically, the numerical modeling gives us the facility to study different operational conditions of a machine or a device or anything of interest. And the benefit is basically minimum cost and risk. Nowadays setting up an experiment and doing all that housekeeping is a cost matter as well as a risk if you are involving in molecular dynamics or many other critical aspects. So, but I also mention you some simulations currently in current context, they consume megawatts of powers for computers. So the actual setup is in micro scale, like maybe some tissues, but the simulations cost us a lot. But there are reasons people do, why people invest. Maybe the one reason would be the higher capability in measurement, because in micro scale level it's so hard to measure velocities, accelerations, pressures, but in simulation we can predict. So those are the benefits. That is common to whatever the numerical modeling. Then I'll move into some more facts on this one, where whatever the numerical technique we use, we need to discretize the domain. What is that? Currently we use digital computers. So if we were to use a digital computer, we need to discretize a problem, whatever the design. The discretization or bringing into some small components of this big problem can be done basically in using grid-based methods or the Meshfree methods. You all, I believe, are familiar in this terminology, finite element methods. You may see that like in solid modeling, you can model an object with finite elements. Like in CFD modeling, flow modeling, we use frequently finite volume method, and even some other predictions we use finite difference method. So in these three, four, whatever the commonly used grid-based methods, the common thing of all these techniques are they depend on a fixed mesh. You can see in most of the cases there's a mesh, and of course there are a whole lot of dominant application which people use these grid-based methods. They are perfectly running perfectly okay for most of the engineering things. But for some special things, the grid-based methods have limitations. So, such as, in case if we were to model a complex physical system, the mesh generation is very costly. It takes days and days to get the first mesh done. It's very difficult. And sometimes if the thing goes large, if we experience large deformations or like for example cracking, if our object cracks, the mesh can destroy or mesh points can degenerate, so which leads to failure of the model, which is costly. And sometimes mesh becomes misaligned with the problem, and even non-continuum material like tissues or different materials, there are some limitation of grid-based methods, and even multi-phase or phase change is very hard. Of course we can do, but it's very costly. So to solve these things, people thought of a different paradigm, which is mesh-free method. Can't we do things without grids mesh? That is called mesh-free, grid-free methods. When it comes to basics of mesh-free methods, these are the key points. They do not involve a so-called mesh, so that is mesh-free. And frequently these methods, they represent a problem using particles. The particles carry properties like pressure, velocity, acceleration. The particles move. If a fluid moves, particles move. I'll show you some examples in time to come. So these 2 points are very important. The properties at any point is evaluated by some average influence of the surrounding particles. And the last point is very important, which is the key difference. Mesh-free methods dynamically computes what are the relevant neighbors. So other than mesh FEM methods is the benefit, we dynamically compute. We'll see. So thereby, due to these key concepts, we can minimize these issues. Rather than many words, I'll show you an example what mesh-free methods can do. You can see this is purely modeled with mesh-free method. You can see particles. This is okay. What is next? That can be modeled with mesh-free. You can imagine with finite element how difficult that would be. In here you can see large deformations, rocks, modeled with mesh-free methods, particles, and what is next? Even that can be modeled. In finite element, so hard. Okay. You can see some other, these are quite well rendered videos I obtained from YouTube. You can see here both solid as well as liquid multi-phase problems can be modeled easily using mesh-free methods. And you can see the next one, molecular cloth, where you can see large deformations. Without much of a trouble, we can simulate and their interactions and the flexibilities. And you can further see these are there. And particularly for fluid flow, people use mesh-free method because you can see during a critical fluid flow, the particles undergo large movements, and they necessarily they form, they deform. You can see bubbles coming out. So with finite element method, it's so hard. Like in extrusion modeling, you can even see. So a whole lot of applications are there. Then yes. So with that background, I'll quickly brief you on what sort of techniques involved. There are many techniques, of course. The most dominant technique for fluid analysis is smooth particle hydrodynamics. I'll give you some more details in upcoming slides. Other than that, you can see, of course, there are a whole lot of, there's about 20-30 lists here. And you can even see most of these techniques are quite recently developed ones. Still they are ongoing. The research is ongoing for further development. We'll go into some more details. In particularly smooth particle hydrodynamics, as I mentioned, this is the most matured one. So I'll brief you on this one. basically. What we have here, so it is basically for fluid flow analysis, and we use a set of particles to represent domain and the properties. Like for instance, if you want to model a domain, we put some particles, we apply some mathematics, and we use some influencing function to get the properties of a given point. For instance, if you want to calculate pressure in a point, we do some averaging, we get some average influence using some function called kernel function. And there are, as usually, in usual case, we use conservation of mass, conservation of momentum in whatever the technique we use. So in SPH also we have similar equations. You can see even that is computed using the particles. That's the only difference. Let me quickly introduce how to model using SPH in a practical application. This is a common common application, common standard problem, Poisson flow. What is that? In two-dimensional, we can apply a pressure on a fluid layer. It's like a stream. What happened? In steady state condition, it creates a parabolic boundary. In steady state, it flows. So in order to model this, this is the fluid, so we can model this with SPH, smooth particle hydrodynamics. The steps are, we initiate the particle, we place some particle in this kind of arrangement. Next, we apply properties like pressure, density, such properties. Then, this is very costly step. This is the most costly step in Meshfree computation, which is nearest neighboring calculations. Because, as I mentioned previously, in each time step, we need to calculate what are the neighbors of each particle. That is very costly. That is done. And we update particle properties, calculate forces. Using forces, we calculate acceleration, find velocity, and find position, which will give you the shape. And we continue our simulation. I'll quickly show you a simulation. This is one done by our research group. And this is the initial particle setup, and eventually it defaults. So it rotates. So it's a laminar flow with very low Reynolds number, very low flow velocity. You can see, yes. Then I need to mention few points on the high performance computing facility, because these simulations are very costly in computational points. We can't run. We can of course run in our computer, but it takes a lot of time and memory. So we usually need high performance computing, like computer clusters, supercomputers in other terms. Basically for, as I mentioned, nearest neighboring calculation. So for instance, for each particle we calculate the distances, so it's a very heavy computation. So for these things, the high performance computing system, basically as clients we submit jobs. Maybe this is in Sri Lanka. In my case, this is in Australia. So I submit jobs from here to Australia using internet. So I submit, there's a server, and like me there are thousands of users. So our first come first serve basis, there's a queue, and we submit jobs for these computer cluster. And whatever the software we request, it uses. In these computation I use C++ with parallel programming. About 12 to maybe hundreds of computers can be used, and it computes and gives me the results. I can download the results that I have used for animations. That is the basic of high performance computing. And it's show time. I'll show you some potential applications of Meshfree methods in different aspects. Particularly, I'll start with tsunami modeling of tsunami waves, which is well related to Sri Lanka. So this is, you can see actual city. Yeah, I'll use the mouse. Yeah, this is actual city. They have modeled using SPH. You can see they have used GPUs 12. I believe you can see, yes, 12 GPUs like processors. This much. They have used 100 million particles to model the flow. So much of particles. So because it's kilometers span. And time steps, and see the hours of 960. So with 12 computers, it took almost 1.5 days to get the results. Okay, I'll simulate. So the wave comes from there, and yeah, it meets the obstacles, and you can see it can nicely predict how the waves go, how the forms, and so forth. We can predict things. Then offshore structures, how they will resist in a large storm. So these kind of form generation simulation is so difficult in finite element methods or finite volume method. Like in these cases, in case if you have this kind of situation, we can even predict how even the solid particles move. So those can be predicted. So these are simulations done by many other researchers. Yeah, and you can see some even the coastal waves can be modeled with Meshfree, and even you can see advanced solid fluid interactions, such as like you can see a whole lot of waves and forms and particles moving back and forth. Even you can clearly see the fluid solid interaction. The fluid solid particles, the solid bodies, they move as interaction. Believe if you were to model this with finite element method, it becomes so hard. That's the benefit. And even large scale simulations, such as aircraft in a accident or some situation, if it were to land on sea, we can predict how the fluid flow goes. So it's a multi-scale model. Huge computations are involved, and we can predict. So people have been using smooth particle hydrodynamics and some other Meshfree methods to model these kinds of setup. Even you can see multi-body interaction in viscous fluid, like this is like I think a chocolate, some flow like with some other particles. So how they interact, and even fluid flow, whatever, you can simulate and observe how the things happen. And even this kind of simulation is possible. You might wonder it is an animation, but there are real physics going behind. In slow motion, you can see multi-body interaction with fluid, solid. That is possible. That's the benefit of these methods. And there's no fixed elements. If we were using it, it will be so hard to use that. And few other things like floating body, simulations you can do. Yes, I'll quickly show you some. In order to compare the results, I'll show you what we can do with finite element or CFD. This is ANSYS simulation of a turbine at a particular velocity. You can see fluid flows, but of course they are actually vectors. We hardly see a fluid flow here, only the deformation. That is a limitation of their particular technique. I'll show you a similar Meshfree one with some other applications. You can see here, these some basics. We'll move into turbines later. You can see we can easily simulate how a fluid interacts with a machinery like this. It's mixing, it's bubbling, all that. Even not only single phase, we can try two fluids without mixing, how they will behave. And you can see particles form, so they are independent. And so different mixing is there. So these are some basic simulation, and particularly in fluid machinery, we can both simulate the solid and liquid here, and you can see how the mixing happening, and not just velocity vectors. We physically see how the fluid moves. That is the benefit. Generally, the Meshfree methods are computationally costly compared to finite element method, because in each time step we calculate what are the neighbors. That is the cost thing. But for these, if we are really interested in a particular problem, we can invest on computational cost. You can see how the mixing going. And now it comes to fluid. Actually, these are basic turbines, but still you can think what are the potential applications. We can physically see how the fluid will behave, not just vectors. And even these kinds of things. So these are basic research. They have not been much used in industrial context up to now, but they are being developed. Even you can see the arrangement. So here, solid fluid interaction, you can clearly see particles coming out as it's meant to be, and with velocity it goes in a trajectory like that. So those are, and in this case the flexibility, we can use a simple arrangement to simulate different flexibilities of different arrangements, solid, fluid and mixing. So these are some benefits. Not only in that scale, we can even simulate like blood flows in capillaries, like micro scale. There are a whole lot of research going on blood cells, particularly in Australia, Singapore. They try to simulate in nanoscale how the fluid will flow, deform. They use SPH for most of instances, where we can model the fluid using particles and observe what is their velocity, and if we change different vein angles in artery angles, how the flow will vary, will there be any possibility for some blockages and all that. So you can see we can dynamically change the angles and observe how the resistance will be there. And not only fluids, Meshfree methods being used to simulate solids, like extreme deformation of thin sheets or material. In this case, they simulate that one. And aerofoils, that is being done. We can the wake flow, attached flow, mixed flow, all that for different viscosities. People have modeled them using Meshfree methods. Turbines, you can see. So in CFD, you will find, or FEM, you will find so hard to simulate how the fluid comes out, this detachment. And may I show you some advanced fluid interaction where flexible bodies involved with fluid. You may imagine this is an animation or something, but there's real physics behind. They have done the rendering nicely. That's why it appears like that. So different particles. So you can see the particle forming. Now, one before the last video, I should mention few points, like these Meshfree methods, other than pure engineering applications, they're being intensely used in movie industry to recreate that real behavior. I'll show you two examples. This is a recently done Disney movie. They collaborate with a university in US to develop basic physics of snow. This is a simulation, but see that real life snow. I have removed the mathematics, but you can clearly see these are Meshfree based simulation. They look real. With different properties, we can do the play with the parameters, and we can get the. So those are the benefits of the Meshfree methods. And even you can see that's the benefit. This is a benefit of numerical modeling. We can change different parameters. We can observe how the snow will behave. Imagine if you were to do this practically, how difficult that would be. And so they change the Young's modulus of snow and observe how things will happen, and to match the best value, even hardening of snow. So different, and in this case, this is real physics simulation, but it's, you can see how the particles move and how solid interaction with other solids, and it's like real snow. So that's the beauty of this technique. And even these kinds of setup they have done. Yes, and they have done some experiments how before with this modeling. Of course, we need to do some experiment to validate. So this is how a snow forms when it moves down, and with this particular model they have done the development up to the next level, and you can see in simulation they have been successful with Meshfree methods. So Disney, they use these for their movie effects currently, and this is the final video I'm going to use for the today's one. This is GPU, processing technique. It's a key conference held in last year. The keynote speech, I'm going to use about 5 minutes from that speech, which is, I believe, very important, and we'll move. It highlights the importance of Meshfree methods in how they use for latest movie animations.
Tiny Z. So what can it do? What can the Tiny Z do? Well, in order to talk about what it can do, I need to go back in history a little bit. 30 years ago, Pixar Animation Studios launched the world into full CGI animated feature films. Russell Jr. 30 years ago was the first animation, CG animation, to win an Academy Award. RenderMan, with programmable shading, played a large role in inspiring us to build a GPU with programmable shadings in programmable shaders in hardware. It took an hour and a half to render each one of these frames on a convex medium. And these scenes, notice they're beautiful. Programmable shading offered really soft lighting, specular highlights, proper lighting, shadows. Everything just looks natural and beautiful. Well, 30 years later, the work at Rhythm & Hughes broke new ground. This is now 2013 Academy Awards Best Visual Effects. It's very, very clear now that generating a beautiful image is not enough. You have to first do the amazing physics simulations. The amazing physics simulations of the real world, so that you could create the mathematics behind water and fire and smoke and particles and collisions before you render it. The unification of simulation and computer graphics is very, very clear now. That computer graphics alone was not enough. The vision that helped us, that inspired CUDA for computer graphics, has really come true. Now, if you compare the work that Rhythm & Hughes did, and this is really amazing, as fast as computers have advanced, in that short time, 30 years, computers advanced 1,000,000 times more powerful. And yet, what took an hour and a half to render per frame now takes 250 hours. The computer has become 1,000,000 times more powerful, and yet it takes 250 hours to render. Well, a lot of that time is consumed in just the physics simulation of the ocean. First, the base simulation, the particles, splashes, foams, all of that composited, merged together in some artistic way, and then, of course, rendering the final image. Well, just as we demonstrated Russell Jr. at Macworld during the launch of the MacBook that NVIDIA was first in, and where the launch of the programmable shader, the invention of the programmable shader, inside our company, the code name was NV20. That particular product launch, Macworld, we demonstrated Russell Jr. in real time. The audience was just floored. Never has anybody seen beautiful graphics like that in real time. Well, ladies and gentlemen, we have a real treat for you today. Jim, let's go through this. So what we're doing here, before we get started, we're doing simulation and computer graphics at the same time. Now remember, first of all, what do you guys think, guys? Hey, how about let's do that one more time for them to enjoy it. Slightly different. Let's let them enjoy it one more time. And then we'll tell them about it. I think I got one up here. So first of all, the wave simulation stirs up the plankton in the ocean, which creates that iridescence. There's all jellyfish all swimming naturally all by themselves. When the whale comes reaching out of the water, it generates, of course, the waves. The wave simulation kicks in. There are 2D grids, there are 3D grids, there are particle systems, there are mist generators and foam generators, and all of that done in real time. As it lands, the wave pushes the raft around, and not to mention the computer graphics, and it's just beautiful to look at.
Yes, yeah, I thought it would be great to have that video. That's why I allocated that much of time. Yes, so that is what is being done, particularly in applied Meshfree cases, where movie industry and some other. Let me to move quickly to fundamental research, which I was particularly involved in, and so that then you can have the full span of idea what Meshfree can be applied. I'm basically expertise in biosystem, basically tissue modeling with Meshfree, and recently we have done a number of publications with in reputed journals, and with Meshfree methods how to simulate a tissue in dehydration, how it deforms. And even recently our work was selected for one of the prestigious journals for its cover page. And let me quickly go through the basics of how we did this using Meshfree. It's the first ever application of Meshfree for drying of tissue simulation. Yes, the basics you can understand that there's a demand in industry for advanced food products where the fundamental understanding of what is going on is important to improve the productivity, even the processing techniques. So in drying, what basically happened, we got a cellular structure. When during evaporation drying, the structure deforms, and so if we can model and we can understand the basics, so that motivated us. And here you can see the structure undergoes large deformation, and it is not a continuous material, it's cellular structure. Thereby it highlights we have large deformations and discrete domain, we have multiphase, gas, fluid, solid, and so forth. So which led us to choose Meshfree methods compared to grid-based methods. And the model, before I explain the basic drying model, there are some literature that people have used Meshfree to model tissues, some single cells, how the fluid escape during extreme deformations. And also, shall I show you some limitations of grid-based methods before I actually show you the Meshfree technique? This is a publication using finite element method published about 6 months back, and you can see they have simulated fresh tissue and dried tissue. But in actually dried tissue, you can see a large sort of deformation in boundaries and so forth. But due to the limitation of the grid-based techniques, they couldn't achieve it. Even the moisture contents only 30% moisture reduction. But with Meshfree, we could do 75 drying, and you can see the boundaries how they deform, even in this simplified tissue. So let me quickly show you how the model was developed and things were arranged. What we do here, we model a tissue as the number of cylinders in 2D, and we model the cell fluid with SPH, smooth particle hydrodynamics, and wall with other method. And we do some whole lot of mathematics to develop cell wall model, cell fluid model, which uses the Meshfree formula. And the concept behind this simulation is we have fresh cells and we let it to dry. Fresh cell condition, a particular moisture removed, it deforms like this. Fresh cell, if further moisture removed, that happens. That is a basic concept. When tissue modeling, we incorporate a number of techniques to assemble a number of cells in a tissue, and eventually we could simulate tissues under drying. You can see how they deform even number of cells. And we found even the numerical or quantitative values were well matching with experiments. So the predictions were quite promising. And not only those basics, even we tried to model different food types based on the structure, and main contribution was the Meshfree methods can do a better job compared to finite element in the current context. This was published in a reputed journal last year, this year. And you can see, depending on the different tissue types, their turgor pressure, all that, the tissue structure deform differently, so which can be easily modeled. And we did porosity analysis when there are pores, how will affect even case hardening with different moisture contents at different cell layers in tissue, how things will vary. Yes, so that comes to the basic conclusions of my today's lecture, where based on my work and also some other videos and evidences I showed you, we can conclude that Meshfree methods have higher capabilities than traditional grid-based approaches, particularly for large deformations, discrete domains and multiphase. But still, I should highlight that FEM techniques are more accurate, efficient in modeling, they are vastly used in industrial applications, that's alright. But for these limited or critical applications, they may not be the optimum selection. There are other ways. Best tool for the appropriate application. What we can do further to improve towards this topic, where I believe further R&D is required to make the computation more efficient. That is a limitation, because we have to do neighboring calculation, which is very costly. Even most of these simulation you saw today are in computer code still. Researchers do fine tuning with this computer program, but we prefer to have nice user interfaces like in our commercial modeling software, so that can need to be done. So those are the highlights, and before I conclude, let me acknowledge some of the key persons or institutions behind me. I should highlight, acknowledge my department Mechanical and Manufacturing Engineering, Faculty of Engineering, University of Ruhuna, who's a young university, young faculty, but it gives immense support to conduct, to have this exposure. And then I should pay my utter respect to my Ph.D. supervisors, Dr. Vijay, Professor Yuan Tunggu, Associate Professor Richard Brown from Queensland University of Technology, Australia. And all my simulations were done in their supercomputer, we call it high performance computing facility, and thanks for them. And I should acknowledge Engineer Anura Muttunayaka, who invited me for this event. Thanks so much. And also Engineer Arjuna Manamperi, who coordinated the event, and the everybody in the Mechanical Engineering Sectional Committee of IESL. Thanks so much. And last not least, the audience being here, spending your valuable time. And thank you.
We had a nice lecture on the Meshfree modeling method. Thank you very much, Dr. Chaminda Karunasena. And now I will wind up the live streaming session. Thank you very much for the live streaming audience. Next, forward with the panel discussion. Today, you can discuss with Dr. Chaminda Karunasena regarding the issues and questions.